Hello everyone, I hope that you are all doing well and have been enjoying the day so far. My name is Iman Bouara and I'm entering my third year in chemical engineering this fall, and today I will present to you what I have worked on during the school year as my UPR project. So I have started working with the CRCT team in summer 2020 for my first internship. I was doing research on the primary production of steel for the recycling process index article, as well as process simulation regarding the recycling of steel through the electric arc furnace. This is where I gained a big interest in process simulation. I have really enjoyed this internship, which is why I continued working with Professor Harvey during the school year for an UPR project, which is about using process simulation for removal of contaminants in steel scrap prior to recycling. So the context of my project is a lot like my summer internship when I was working with the recycling team. So as the science community's interest is more and more leading towards a circular economy, the recycling of metals is an interesting field to look into. And a lot of times we hear that metals can be recycled an infinite amount of times, but that is not always the case. A lot of challenges can appear to make the process of recycling more complex, which is a good part of the research that I'm doing. So the main goals of my project were first to analyze the two main ways to recycle steel, which are the electric arc furnace and the basic oxygen converter. Then the second part of my project is focused on the presence of contaminants, which are an obstacle to recycling. Then I will gather all the information and results from simulations to write my section in the process design paper, which is about how to use thermodynamic concepts to do process simulation. So scrap can be introduced in the two pyrometallurgical ways of primary steel production. It can be added to the basic oxygen furnace as a coolant, since most of the reactions occurring in that furnace are exothermic. There is around 25 to 35% of scrap added. The other way to recycle scrap is through the electric arc furnace that can have up to 100% of scrap that will be remelted into liquid steel. The steel production right now is at around 72% for the basic oxygen furnace and 28% from the electric arc furnace. So regarding the electric arc furnace, it can use 100% of scrap to recycle it into new steel, but in a lot of cases, contamination can cause the addition of a new step before the scrap can enter the furnace. We need to have a certain control over the chemistry of the scrap in order to recycle it, and contaminants are usually the first barrier to an efficient recycling of steel. So two contaminants that we find a lot in steel scrap are copper and zinc. Copper is a secondary alloying element which is added to increase the steel's corrosion resistance and mechanical strength. But it also decreases its hot rolling resistance, which is why it should be removed before it gets remelted. The contamination of copper is mainly from end-of-life vehicles and electronics. Zinc is a tramp element and gets into the steel through a process called galvanization in order to protect the surface of the steel from corrosion. So copper and zinc cannot be removed through oxidation only, but the use of a mixture of chlorine gas and oxygen is a way to remove them. The method of oxychlorination is basically the use of solid gas reactions to remove impurities using the contaminant's affinity with chlorine gas. So the gas mixture enters the reactor at standard conditions of 25 degrees and 1 atm. A temperature of 800 degrees inside the reactor is optimal to assure a bond between the oxide layer and the scrap, as well as to assure a high enough vapor pressure of the chlorides. The ratio of gas rates between air and chlorine is 10 to 1 in order to have a molar ratio of 2 to 1 for oxygen and chlorine. This ratio is chosen to promote the formation of an oxide layer, while zinc and copper are removed by chlorine gas. The formation of an oxide layer will also avoid a phenomenon called copper deposition, where the concentration of copper chlorides is too high inside the reactor, which will cause its reduction back to copper. That will be prevented by the oxide layer forming at the surface of the scrap. Also, having ferrous oxides is a lot easier to convert into steel rather than ferrous chlorides. The method of oxychlorination has numerous advantages. In fact, chlorine gas is cheap and available. Volatile chlorides are easy to separate, and so there are ways to recycle both the gas and the contaminant. Also, using gas-solid reactions means that it provides a better surface contact and so better removal. Now, since the process design paper is based on using thermodynamics, I need to apply some of the concepts learned in my class in my simulation. In a lot of articles that I read about this experiment, they would generate phase diagrams to predict which products will be formed, and I thought it was a very interesting approach, and it relates to my project, so I decided to do the same thing. But first, I need to find the partial pressures of both components of the gas mixture. So to do so, I generated an equilibrium module representing the gas mixture that will be sprayed onto the steel scrap. Since I know the ratio as well as the temperature and pressure at which the gas will be, I can just create this mixture that will represent my gas phase. So in the results page, I can see the gas, the amount, and their respective fugacities. As learned in the thermodynamic class that we did last fall, we learned that by the Lewis rule, when the pressure is very low, in my case oxychlorination is done at 1 atm, then the fugacity of the gases is equivalent to their partial pressures. Now that I have the values of the partial pressures, we can now use the phase diagram module in order to generate the wanted phase diagrams. Since the elements important in the simulation are iron, copper, and zinc, I did a phase diagram for each element as a function of the partial pressures of both oxygen and chlorine in the gas mixture. It's important to mention that a very high pressure was imposed to generate those diagrams in order to see the stable domains of the copper and zinc chloride phases. So the products that will most likely form is Fe2O3, CuCl, and ZnCl2. So as we see, a little bit of iron is going to oxidize, but as I mentioned earlier, it will create a protective layer on the scrap to prevent the chlorination of iron as well as copper deposition. So what's next for the project? The articles should be done for December, most likely, while we take the time to finalize the simulation and the writing of the article. So that's going to be it for me. I hope that you enjoyed this presentation. Here are my informations if you have any comments or questions. So thank you guys so much for listening, and enjoy the rest of the day.